All right, guys, so today we are going to cover the acid-base balance. While it says this is lecture 10, it really can go in two different places in our body, and we can talk about it in two different areas. One, dealing with our respiratory, which is what we're doing, and two, we will look back at it when we get into the urinary system, again, because this has to do with acid-base balance of fluids in and out of your body. So, I just wanted to go ahead and talk about it now because I think it lends itself well into when we are talking about, for instance, respiration. We talked a little bit about carbon dioxide and oxygen levels and looking at altitude sickness and whether you have the bends or not. With nitrogen buildup. And again, a lot of this has to do with our buffering system and whether our body is more acidic or more basic. So we've talked briefly, right, that in terms of pH, our body is naturally anywhere between 7.2 and 7.4. In other words, we're pretty much neutral, right? So on a pH scale, neutral is 7. Anything below 7 is what we term acidic. This word right here. Anything that is higher than 7, we term it basic or alkalinic. All right. And that just means that if something is more acidic, it has more hydrogen ions. If something is more basic, it has that hydroxide ion. If you've taken a basic chemistry class, this should look a little bit familiar. If you haven't taken chemistry yet, please do. I think it is vitally important and for your understanding on why sodium is a positive, why potassium is positive, why chloride ions are negative, why calciums are 2+. So you start to realize where these numbers are coming from, and I'm not just making them up in thin air and saying this is what it is and you should do it. All right, so also looking, my bad. An acid is a substance that dissociates to release hydrogen ions. So what we also say is an acid is a proton donor. And again, H+ is a proton. So anything that donates that H is an acid. So prime example, HCl, hydrochloric acid, hydrosulfuric acid, HS, phosphoric acid, H3PO4. So some of these H whatevers, specifically that last column in the periodic table, your halogens, those are going to be your strongest acids, all right? A base is then anything that accepts a proton. So acid donates, bases accept. So a chloride ion, Cl-, would be the base. Water can be a base or an acid depending upon which it's going to be in a reaction. So we even can say water can be an acid or it can be a base. So look over some of those. Again, I'm not going to say which one of these is an acid, which one of these is a base. That's not the point of this class, but I want you to be familiar with some of your terms going forward. Salt is just anything that precipitates out in solution. And the big kicker here, which what we're going to look at, is a buffer. And a buffer is a substance that tends to oppose changes in the pH. So if we all of a sudden get in a condition or a situation where we become more acidic, a buffer is going to be able to oppose that acidic environment and changes back more to being alkalinic or basic. Same thing if we get in more of a basic situation. That buffer system is going to bring us back down the pH scale and make us more acidic. Not that it's going to all of a sudden shift us down to a pH level of 1 where we're literally acid soap or lye, or I don't even know. I think there might be a chart in here about some different kinds of which one is acidic, which one is basic. But like coffee I think is around a pH of 5. Lye soap is a pH of like 13. It's very basic. That's why it burns. Bleach is something around like 13 or 14. Tomato juice is around like 4. So things, even just things you naturally eat, well, hopefully you're not eating bleach or lye soap, but tomato juice and coffee, those are acidic. That's why the enamel on your teeth can get worn down and you can get stains on your teeth and your dentist yells at you. Also, your stomach acid, your gastric juices, which we will talk about next week with digestion. Your stomach is right around pH of 2. So anytime you throw up, right, it burns when it comes back up because you're throwing up the acid in your stomach, and it feels like your throat is on fire, especially if you throw up, more than, let's say you just got a stomach bug, you got food poisoning or something, and you were just constantly throwing up for 12 hours straight overnight. The last thing you want to do is have anything else come up your throat. You want something cold going back down it to soothe it, right? So that's why a lot of people take antacids, right? Pepsid, Tums, what's that purple pill, Nexium. A lot of people take these antacids in order to decrease the activity of those gastric pumps and hopefully then not bring about the so-called heartburn. Again, we'll talk about that when we get to the digestive system, just kind of giving you a highlight of where other acids are in your body. All right. So different classes of acids. We have fixed acids. These are acids that do not leave solution. Once they're produced in the body, they're eliminated, and they remain that way until they're eliminated by the kidneys. Metabolic acids, though, are acid participants in cellular respiration. So this would be pyruvic acid, lactic acid, ketone bodies. We'll get into all of that when we talk mainly about cellular respiration next week. And then your volatile acids. So these can leave the body, entering or exiting the atmosphere at the lungs. So this volatile acid part is what we're really going to focus mainly on today, because we're going to be talking about respiration, or we already have covered a little bit of respiration with CO2 and hydrogen being water, then to carbonic acid, then to bicarbonate ion and a hydrogen ion. So that's where we're looking today. And a lot of this rest of this PowerPoint there are going to be slides up, but I'm going to be really talking more about kind of where I'm thinking you all need to be at. So let's look at the partial pressure of CO2 and blood pH. So remember, carbon dioxide, like oxygen, moves from high areas in concentration to lower areas of concentration during when we breathe, right? So we looked in class and looked at respiration, and in the alveoli, we have that exchange where in the alveoli, hopefully you have a high concentration of oxygen, and in the blood, in the capillaries, you have a low concentration. So those oxygen ions are going to move across that threshold into our blood and then be taken to the rest of the tissues, and then oxygenates our blood, specifically in that pulmonary vein, and then that can go back through the heart. We looked at that, into the left atrium, through the mitral valve, into the left ventricle, out the aortic valve and aorta, into the rest of the body. But in our alveoli, because we have a high concentration of oxygen, because we just breathed in, yes, I just did that on microphone, you have very little carbon dioxide, unless you're literally, breathing your gas pipe or your muffler. That this would not be good. That's carbon monoxide, but still, it's a form of a gas. As long as you're outside breathing, for the most part, you're getting more oxygen than you are carbon dioxide. So there's a lower concentration of carbon dioxide in your alveoli, and there's a high concentration of it coming from that deoxygenated blood, the pulmonary artery, bringing it to the lungs, and therefore you have that simple diffusion where the carbon dioxide leaves the capillaries and enters into the alveoli, and then when you breathe out, you're breathing out CO2. All right, so CO2 is found in the blood in 3 different forms. Make a note of this. So CO2 can be found in dissolved. So 10% is about dissolved in plasma. 10% is dissolved in the plasma. 30% is bound to hemoglobin. And that is because hemoglobin actually has a higher affinity for CO2 than it does for your oxygen or anything with CO. So this is why carbon monoxide poisoning and cyanide poisoning are deadly and can be deadly. Really, it has to do with the carbon that's attached. As long as there's a carbon attached, hemoglobin loves it. They become, I don't know if you ever played with, if you were that kindergartner who put glue on their hands and then stuck them together and saw how long it would take for them to stick, and then they stayed stuck. And then when you ended up doing it with like your mom's nice like tacky glue and they really stayed stuck for a good long time, not as fun as Elmer's glue, because Elmer's glue kind of comes apart. But yeah, anything with carbon will get attached to that hemoglobin and stay and not want to be released. And that is deadly, right? Because then you're not able to move the oxygen efficiently. All your body is doing is carrying carbon dioxide and it's not getting rid of it. And therefore, all of your tissues then become deoxygenated and you end up almost in a weird way suffocating while you're still able to breathe. Does that make sense? I know that kind of seems a little weird, but in essence, you end up suffocating yourself. All right, so that was 30% can be bound to hemoglobin, and then 60% is in the form of bicarbonate ions. So if you don't know what a bicarbonate ion, it is HCO3 minus. This is a polyatomic ion for those of you who have taken chemistry class. And again, this is our buffer system form. So CO2 will get together with water. It'll create this intermediate form, which we call this carbonate, and then it'll quickly be transferred over into our hydrogen ion and our bicarbonate form. So this therefore means as you have more CO2 present in your body, you're more acidic. Your pH drops. Follow this equation here, and if this increases, you're going to push the equation toward the right and create more hydrogen ions. And again, if we go back to our terms here, remember acidic means we have more hydrogen ions in solution. All right? If we have a lower amount of CO2 in our bodies, we actually then don't end up going through this reaction per se, but we become more basic. Our pH actually rises. We have less hydrogen ions present, and we actually have more kind of water ions present. I don't know if water really forms an ion. It's called hydronium, but don't worry about it. Or deuterium. Squirrel moment there, guys. And so therefore the lower CO2 levels, the more basic you are. And the reason this becomes important is when we talk about hyper and hypoventilation, right? If you're hyperventilating, what do you think? Do you have more CO2 in your body, or do you actually have less CO2 in your body? I'll give you like 5 seconds to think about that thought. All right. I hope you said when you are hyperventilating, you actually have less CO2 in your body. You're blowing it all off, right? You're rapidly breathing and you're not able to get a good full breath of oxygen in, and so you're blowing off all of your CO2. Therefore, the less CO2 you have, the higher your pH starts to rise, and you're turning yourself more basic. This is what we call respiratory alkalosis. We'll look at a little bit more in depth with it here in a second. But this is why they give you a brown paper bag to breathe in, and they say breathe into this brown paper bag. It's going to regulate your breathing. Here's why, right? If you put a brown paper bag and you start breathing in a brown paper bag, if you weren't able to understand that, it's because I had a brown paper bag over my face. And what's that doing is you're blowing all of your CO2 into the bag and it's not able to go anywhere. It's trapped in its little container of the brown paper bag, and it's forcing you to breathe it back in. Therefore, you're breathing in the CO2 and trying to get more CO2 back into your system, and therefore bring your basic level back to more of a neutral stance, hopefully also reversing that fast breathing, that hyperventilation, and bring it back down to more of a natural flow of air. Does that kind of make sense why they always give you a brown paper bag when you start to hyperventilate? It's also the reason you start to pass out. You don't have much O2 in you, and you're also breathing out all of your CO2. So you get lightheaded and winded. You just don't have anything going in. All right. On the flip side of that, hypoventilation. So if hyperventilation was an alkalotic state, hypoventilation is an acidic state. Thank you. All right. So that's because when you breathe in and you hold it in and you don't let it out, all you've done is you're actually increasing the amount of CO2 in your lungs because you're not breathing it back out. And therefore, again, looking at this side of our equation, the more CO2 we have in our body, we push this equation to our right, and we create more hydrogen ions trying to balance it out, and therefore we become more acidic. All right, that was just a little quick spiel on that. Again, we'll look at that here in a second, maybe break it down a little bit further. But so how is all of this sensed, right? So we have these buffer systems, and they sense them based on chemoreceptors. So we have two types of chemoreceptors. We have peripheral chemoreceptors. These we talked a little bit about in the heart. I told you that there are also baroreceptors in our heart, but these chemoreceptors are located in the aortic arch and the carotid bodies, right? So those are our three main artery vessels that are coming off of the aorta. All right, these peripheral chemoreceptors, and again, chemo is sensing chemical changes. We should have learned that back in 168. These are stimulated by a fall in the partial pressure of oxygen. So if all of a sudden you have low pressures of oxygen or low partial pressures of oxygen, these are stimulated. They are also stimulated by an increase in hydrogen ions or a decrease in pH. This should make sense. If you have a fall in partial pressure of oxygen, you're also likely increasing your carbon dioxide amounts. And again, an increase in carbon dioxide means that we're going to get an increase in hydrogen ion quantities, and therefore we're going to become more acidic. I know that was a mouthful, but again, we're just adding just little chunks onto everything we just talked about, all right? And thirdly, well, that's what I really just stated, so don't worry about that. Peripheral aortic bodies, aortic arch and carotid bodies, stimulated by a fall in the partial pressure of O2 or by an increase in hydrogen ions. And that hydrogen ion increase is likely due to an increase in CO2 levels. All right. The other type of chemoreceptor that we have are our central chemoreceptors. These are located in the medulla of the brainstem. All right. They do not respond to changes in oxygen levels. All right. So they have nothing to do with O2. And they do not respond to changes in hydrogen ion concentrations. All right. Because hydrogen ions do not cross the blood-brain barrier. All right. Blood-brain barrier is very specific. It's made, remember, by those astrocytes, which are part of our central nervous system cell. Hopefully you kind of remember some of that in your nervous system. Sure we do, Miss Burke. Got it. But they do respond to changes in carbon dioxide levels, because carbon dioxide can cross the blood-brain barrier. And again, this kind of goes back to the whole, if you want to, breathe your muffler pipe in, I don't allow that, and I don't condone that. Well, I do condone that. That's bad. Don't go breathing your muffler pipe. But if you do breathe that in, a lot of times that why there is brain damage in individuals who stop breathing. You have a lack of oxygen, but you also have a buildup of CO2. CO2 can cross that blood-brain barrier, and CO2 does not do well in your brain. It does not play nice. Okay, it starts to destroy tissues, which leads to then dark spots in your brain, and you can see a lot of death, a lot of tissue death. And so that is why if somebody is found not breathing, they're unconscious and not breathing, a lot of times the first thing you need to do and what you're really wanting to do is try to get them as much pure oxygen as possible, as quickly as possible, to try to weed out that CO2 out of the brain. All right, cool stuff. I think that kind of covers it for the two types of chemoreceptors. I don't need you to know much any more than what we've probably talked about in class and then what we talked about here. But now we're on to the actual physical acid-base balance. I know we've already kind of shown it, but the acid-base balance has to do with, normal ranges. So this is normal ranges in our plasma, right? So again, your normal range for pH is anywhere between about 7.3 and 7.4. It can go up to even 7.6. So don't think that, oh my gosh, it's getting towards 8. I mean, really, in retrospect, they're still neutral. All right, that's still pretty neutral. Your normal bicarbonate ion concentration is anywhere between 21 to 27 milliliters per, I don't even know what it is, but don't get caught up with these numbers. I'm just giving you an offshoot in case, you're in your clinicals and you're looking and they're like, oh, wow, their bicarb is extremely high, or, oh, it's extremely low. And you can then kind of have a base number to look at that from. And again, PCO2, I know we talked about this in class, is the normal range is anywhere between 35 and 45 millimeters of mercury. And again, we measure this in millimeters of mercury because that is a pressure gauge. There we go. All right. So how do we control pH changes? All right. So the first way is via the metabolic way. Again, I don't want you to go into too much depth with this today because we will revisit it when we look at the kidneys and the urinary system. But kidneys secrete or conserve hydrogen ions. All right. And they're used for long term. So if you are undergoing, chronic alkalosis, or you are a diabetic and you are ketoacidosis, or acid, however you would say that in the present tense. But if you have ketoacidosis, your kidneys are functioning to combat that, and that's chronic, right? And the issue then is this takes a lot out of your kidneys. So then that's why, if you're ever in that ketoacidotic state, what ends up happening is a lot of times you're doing a lot of damage to your kidneys, and therefore you'll see a lot of diabetics end up needing kidney transplants later in life if they don't regulate their sugar levels properly. All right. The other type of buffer system we have is our respiration buffer system, and we've already mentioned a little bit about it, but it can change the levels of CO2 retained or leaving the lungs. And so this is more short term, all right? So if all of a sudden you're making more CO2, the next thing you know is you might start hyperventilating in order to blow off all that extra CO2, all right? So we have different types of buffer systems. Again, we are mostly talking today about this carbonic acid buffer system. And you can see here's the amino acid buffer system. I'm not overly concerned you understand that. Here is your carbonic acid buffer system. So this is the one we are looking at. So you breathe in CO2. CO2 can combine with water to make that carbonic acid or carbonate. And then it can go through making hydrogen ions and that bicarbonate ion. All right. Now notice that there are blue and red arrows. This whole reaction is reversible. So it can go either way. It's not a fixed one-way street kind of thing. All right. And then the fun part about this is that sodium can team up with bicarbonate ions to make sodium bicarbonate, which ends up then being a salt, and we can excrete a lot of that in our urine. All right, so this is how the respiratory system interplays with the urinary system pretty finely and, in fine tune. And we'll also see when we get into the urinary system, we'll talk about the RAS system, the renin-angiotensin-aldosterone system. And we'll see that the lungs actually are a main player in forming the ACE, which is an enzyme that ends up breaking angiotensinogen into angiotensin 1 and then into angiotensin 2. And so the lungs are very intertwined with the urinary system for whatever reason. They share a lot of similarities in how they help to regulate the body. So again, it kind of all goes back to this whole notion that you don't want to mess up your kidneys, right? So we've talked a lot about, the brain is really the powerhouse and we can't do anything without the brain. And you can't, really. I mean, you can be brain dead and they can still put you on life support and still have you going. And, we talked last time about how the heart, you need a heart in order to move blood and therefore stay living. But I would have to say, then next in line behind brain and heart, there's a really fine battle going on between whether it's respiratory system or whether it's your renal system, the kidneys, in fact. And really, you can break the kidneys away from the urinary system and just really call them the renal system. And that's why a lot of nephrologists, right? Those are the individuals who study the kidneys and look at the kidneys. They make bank, all right, because they're able to understand why certain drugs are filtered and not filtered and excreted and secreted by the kidneys, and how different changes, and we're talking minute changes, can have huge effects on the kidneys, right? So we've might have mentioned, and if not, we're going to talk here. This is one of my little, we're taking a detour kind of routes here. But a lot of drugs that we in the first world problem generation have taken do a lot of damage to our kidneys. And if we're on a lot of these drugs long term, we have started to see, and studies are showing, that we can have kidney damage, and major kidney damage for that fact. And for a while, and not for a while, but we've been told within the past, 10, 15 years, you have to stop taking so much Tylenol. Tylenol does havoc. It wreaks havoc on your liver. You can end up going into, serious liver failure and cirrhosis just from taking freaking too much Tylenol. Ibuprofen can do a whole number on your stomach if you're not careful, if you're not taking it with food. But also ibuprofen can do a whole heck of a number then on your kidneys, right? Your kidneys do not process ibuprofen as nicely as it does acetaminophen, Tylenol, right? So while acetaminophen, gets stuck up in your liver, definitely if your liver is really not functioning, but it starts to clog it up. But the kidneys can get rid of it once it gets processed in the liver. But ibuprofen, even if it gets through the stomach, it still does not get processed as nicely through the kidneys. It can start to back those up, and they start to lose function. So anytime you've seen individuals on, these high doses of ibuprofen, 1,600 milligrams, and, technically hopefully they're only, taking it while maybe they're in the hospital or just come off of, major surgery. But if you're talking about it, you got kids now that just go into mom and dad's medicine cabinets and start taking all the pills that they want to. And who knows what other side effects those have. But you think about it, you get 200 milligram tablets of Tylenol or ibuprofen or Advil, whichever one you choose. Even if you took 8 a day, You're at 1600 milligrams without even like a sweat. You haven't even broken a sweat. You do that over a course of several years. I mean, you're really backing up your kidneys. And so this is why we have a lot of these new age diseases and disorders coming along. It's because we are abusing some of these drugs that we invented and found that work great with pain, but they don't do great on other organs of our bodies. All right. I know that was a total side tangent. I apologize for anyone who had to like listen to that, but just know your lungs and your kidneys work very well hand in hand. You don't want to mess up either of them. All right. So the next slide, don't worry about it. You will look back at it when you get into the urinary system. This was the interaction, so it shows you how the lungs and the kidneys work pretty freaking well together. Now moving on to some of our disorders. I wanted to quickly mention your metabolic disorders, which again can be broken down into metabolic acidosis and alkalosis. Metabolic acidosis occurs from ketones, all right? What are ketones, people? Hopefully you know this, and if you don't, we will talk about it probably next week when we talk about the breakdown of fat. But it is what is made. It is a protein that is made, not really a protein, it's more of a chemical, it's a dissolved chemical that is made from the breakdown of fats. All right. And so the more ketones you have, right, the more likely you are burning a lot of fat because it is a byproduct of fat. It's like C with two R groups and double bonded to an O, if you know any of your organic chemistry. If not, don't worry about it. I'm not going to ask you the structure of it. But it is an organic molecule. That's the word I was looking for earlier. All right. So metabolic acidosis can be the result of the formation of a lot of ketones from exercise, carbonic anhydrase inhibitors. I know you don't necessarily know what those are maybe, but if it is a carbonic anhydrase inhibitor is actually ceasing the breakdown of those carbonic acids, all right, that carbonate, that H2CO3, all right, and big kicker here, you can get metabolic acidosis from having a bout of diarrhea. Let's say you have like 2 to 3 days of bad diarrhea, right? You're losing intestinal bicarbonate, and therefore when you lose that bicarbonate, let's go back up here to our equation. If you're losing bicarbonate, right, you're actually then retaining more CO2. Not necessarily that you're retaining it, but when you lose this buffering system, right, this is actually then making you more acidic. All right. On the flip side, metabolic acidosis is typically due to the ingestion of a heck of a lot of laxatives, diuretics, antacids, right? Because all you're doing is you're keeping your body from producing its normal gastric acids, right? And again, diuretics and laxatives, you're not necessarily getting rid of the bicarbonate, but you're causing your body to lose a lot of the CO2, believe it or not. But the big one here is metabolic alkalosis is primarily seen with, again, taking a lot of antacids, so Tums, Nexium, Prilosec, all of that, but also then vomiting. You know, you have, the stomach bug for 3-4 days, you're out, right? And you've just been constantly throwing up. Again, you're probably more in a metabolic alkalotic state at this point because you don't have any gastric acid juice anymore. I mean, your body has upchucked all of it. And so now it is undergoing this alkalotic state, and we have to then go back to our buffer system and try to bring us back towards a neutral. All right. So the big ones here within the respiratory system, we have respiratory acidosis. This is again due to hypoventilation, so we're retaining a heck of a ton of CO2. This also is from inadequate alveolar ventilation, the overproduction of CO2, whether we're increasing it because we decided to put on the wrong tank, and instead of picking up a pure oxygen tank to go scuba diving with, we picked up a CO2 tank. That would be bad. If you're deciding to huff in a lot of helium balloons, you're actually probably increasing your CO2 levels as well, and therefore you're going to get lightheaded. You sound funny because helium is less dense than oxygen, but again, because you're retaining those hydrogen ions, you're actually pushing the buffer system towards then keeping in more CO2, and you are actually more in a respiratory acidosis state. All right. Respiratory alkalosis is due to then hyperventilation, which we just talked about, which is an excessive loss of CO2. This typically is seen at high altitudes, right? So if you go to try to climb Machu Picchu, I don't know how tall it is. I think it's somewhere like in the 10,000 feet above sea level. The thin is very air. Excuse me. The air is very thin. You do not have a ton of oxygen to breathe up there. The partial pressure is much lower, right? So then typically you're going to start to hyperventilate. We've talked about this in class. You start to hyperventilate in order to get more oxygen in. You're going to breathe faster. This is why if you go climb any of the mountains out, not here in the Appalachians, we don't have, that high of mountains per se, but in the mountains in Colorado, I can't think of them for the love of my name right now. But anyhow, out west, right, those mountains are still growing. They're getting bigger and bigger because of the tectonic plates that are colliding at that junction and actually continuing to build up all of our mountains out west. Whereas our mountains here are being eroded because of the subduction. But again, that's geology, not physiology. But if you go climb anything out in Colorado, Montana, Utah, even parts of Arizona, you might notice you're all of a sudden going to get to the tippy top. And besides the fact that you just hiked maybe 8 miles, you're also going to be breathing heavier, especially if they're really high up. I mean, I think when my family and we went out to Zion National Park out in, I don't even know where it is to tell you the gosh darn truth. There was one hike. One was Angel's Landing and the other one was Observation Outlook, and both of which were somewhere around 10,000 feet above sea level when you got up there. And I can still to this day remember, how in pain I was because we were probably experiencing altitude sickness. We were breathing such thin air and air that just did not have the oxygen level that we needed. So we were breathing much heavier. And so we were throwing ourselves into a respiratory alkalotic state because all of our CO2 was also leaving, right? All right. That was a little side note, and we probably already talked about that in class. So you probably just heard the same story twice. I apologize. But, alkalosis can also be the result of a head injury, stroke, pain, fear. You could be hyperventilating due to peripheral chemoreceptor stimulation. Remember, those peripheral chemoreceptors are located in the aortic arch in the carotid bodies. You could be respiratory alkalotic due to an embolism or edema, right? So these are some of the things you might start to see in your clinicals when you're doing your actual practice. So I just wanted to throw those out there for you. This slide gives you a nice little thing of all of these disorders that you can then look at and check and see. But the main thing I want to break with today is how does all of this compensate? So if you are in an acidosis state, so you have too much acid. If you have too much acid, therefore you have high CO2 levels, and you have too low, oh, excuse me, if you have too much acid, there we go. So high CO2 levels, the problem is a respiratory problem, and therefore to compensate, we're going to either start to breathe faster or slower, depending upon. But long-term compensators will be the kidneys, right? So the kidneys are actually going to start to get rid of the bicarb, specifically if you have too much acid. If you have too little acid, so you're not getting enough CO2 in, right? Again, it's a respiratory problem, but the kidneys are going to be your oversight and help to then keep in the bicarb. The flip side of that then is if you have too little or too much base, again, this is a metabolic issue. So anytime we see CO2, think it's a respiratory issue. Anytime you see bicarbs, HCO3 minus, think of this as a metabolic issue. And again, respiratory are going to be your quick effect dealers or compensators. The kidneys, again, though, are your long-term compensators. So again, kidneys and lungs kind of go hand in hand. They're best of buds. They can't really function without the other. And again, this lecture, I wanted to get this not over with, that sounds rude, but I wanted to get this brought up to you because, again, you will see acid base a little bit when we get into the urinary system. We've kind of already mentioned it, so I'll see if I even put it in the urinary system, but I would like you to definitely know it once we get back into that system. But this then should sum up the respiratory system. We had lecture in class. This is your final one of respiratory. You should be A-OK to go ahead and take your quiz. Again, if you have any questions, don't hesitate to contact me. I'd be happy to explain anything a little bit further in detail. All right, that's it.